Hello, everyone. I'm Denis Firsov, a research scientist from Matter Labs, and I will tell you about how do we use formal methods to harden and prove properties about ZK-rollups. So let's start with the motivation. ZK-rollups are famous for their slogan that zero-knowledge rollups bring scalability without compromises in security. And in this presentation, I kind of walk through the journey of seeing if and how much is this true and what is being done to make it true. Okay, so first, scalability. Scalability is very visible and gets a lot of attention. So it's easy to check, it's easy to verify by even by the users who see the TPS, the number of transactions, the downtime, and all this type of metrics, which are very visible. At the same time, security stays invisible for quite a long, essentially, unless you're hacked or there's critical vulnerability, not many people care about security. So does it remain a promise or not? And what are we doing to gather the evidences and guarantees to prove that we actually have security in our system? All right. So the list of evidences could consist of many things. Clean documentation is one of them. This at least guarantees that the developers and and team who is developing the rollup actually understand what they're doing, and everyone is on board. The systems are usually being tested and audited by different outside companies, and then we can ask whether these evidences are rock solid and conclusive. And does it actually make sense to ask for more? So what are the troubles with testing and auditing? Testing and fuzzing type of techniques, they can help shallow programming and correctness mistakes and bugs, but they're rather meaningless for security properties of cryptographic protocols, like let's say zero-knowledge, soundness, and proof of knowledge. Of course, they are almost never conclusive. So though doing testing and fuzzing could be important to gain the guarantees, and everyone should do that, but you don't get the final guarantees of security and correctness. With auditing, a lot depends on the quality of code which is being audited, on the time spent, and the expertise of the auditors, and the result is usually as well never conclusive. But for the critical components of the system, we would like the conclusive proofs of security. And now let's look at the ways how to do that. But first, there is a trouble with security proofs because in principle, in theory, once the protocol is proved secure, it is secure forever. But in practice, what happens is that security proof is wrong or the implementation is broken. So we need to account for these possibilities and then arrive at some kind of end-to-end security guarantees where we would verify our theory, but at the same time connect it with the implementation. So this is the challenge. Also, many people in the space of design of cryptographic protocols have noted that we are living in the era of crisis of rigor because we produce protocols which are conceptually much more complicated than in early days, and verifying their security and correctness proofs becomes very, very hard / impossible by just randomly assigned 3 reviewers at the fancy conference. So something must be done about it, and one way to enforce rigor is through use of formal methods. So for the people who hear about this for the first time, the main idea behind formal method is to implement formal logic as a computer system, which is usually called theorem prover, in a similar way as we do for programming languages. And in this way, the proofs are implemented by humans, but checked automatically by a computer. And this is important because it's still, the main insight here is that it takes a human creative being to write a non-trivial proof, but the computer can efficiently verify your proof, check whether your proof is correct, without any kind of compromises. So let's try to use formal methods for ZK rollup, and then if we do that, we immediately face a couple of challenges. So first challenge is that trusted code base of zero-knowledge rollups is huge and is growing essentially every day. As we are speaking right now, some programmers are adding lines of code to the TCB. So it's very clear that it's impossible to formally verify our entire code base. So we must be very careful and find and focus on the critical targets, which brings the most trust and the most security. There are many possible targets, which you see on the slide, and all of them are important in one way or another for operation of the system. But arguably, different targets have different amount of conceptual complexity behind them. So, for example, rollup contracts which are deployed on layer 1 are definitely critical components, because that's what defines the governance and the bridging and so on and so forth. But conceptually, this is not too complicated piece of code. At the same time, virtual machine and semantics of the virtual machine could be huge and worth actually formalizing and describing in formal terms, so that we know that our implementation actually has some declarative specification. But in this talk, I will focus on the zero-knowledge verifier as one of the most critical and conceptually complicated pieces behind the rollups. And this is for the following reason. So for the most rollups, all the assets of which are stored on the rollup are guarded by a verifier contract, which is deployed on layer 1, and which checks the zero-knowledge proofs which are submitted to it. So for this system, verifier is the ultimate source of truth, and for that reason, it is vitally important to prove that this contract is sound. Whereas by soundness, I mean that it doesn't accept the proofs of false statements. Proof of knowledge would be even better. Another point is that this soundness proof is critically important for decentralization. So as long as you have a system where you submit proofs to the verifier which you generate, you're safe. Not much can go wrong. But the moment you go decentralized and any adversarial actors can submit random proofs, you better be sure that your verifier wouldn't accept proofs of the false statements. But let's review what are the challenges. So here is the Plonk verifier, or the final stage of the Plonk verifier, which is written in LaTeX. Yeah. So it's very beautiful, concise, abstract definition, which is expressed on the very high level of abstraction of mathematical structures like groups, fields, and so on. And it's very pleasant to analyze this type of description. But when we go to the actual implementation, which is deployed on the L1, then you'll be faced with 2,000 lines of low-level handwritten assembly in YUL. YUL is a particular language in which this type of contracts are being implemented. And what you see is the 1% of that verifier. So clearly, but why is this important? Another reason why is this important is that lots of security relevant decisions are done by the developers, which are not specified in the paper. So at the moment when whatever talented software engineer plans to implement this type of code, he must make lots of decisions, which he cannot consult with pretty much anyone. The example of the decisions would be how to encode data. Does the encoding matter, especially for security? Can he come up with the encoding of data which would break zero-knowledge property, for example, or not? The quick answer is yes, he can. How to implement group and field operations? What to do if prover sends garbage? Is it always safe to abort? You also don't want to implement the naive implementation of the verifier, but you would like to optimize it. So can anything go wrong in this process? So yes, yes, and yes. And there are many other decisions which are being taken on that journey. So what is the challenge? The challenge is how do we prove that the Joule verifier, namely this assembly low-level verifier, corresponds to the latter verifier in the paper. And to of course make any kind of formal proofs, we need a theorem prover. We need to decide on the tooling which we're using. And for this particular task, we believe that EasyCrypt theorem prover is the good choice because it was designed exactly to handle cryptographic proofs in a computational model. Moreover, it incorporates specialized program logics in which you can reason about pre and post conditions of the imperative modules, which are very close to what you write in Joule. So a lot of Joule code could be just copied and pasted with some syntactic changes from one environment to another. Of course, EasyCrypt also allows you to specify cryptographic assumptions and prove correctness, and most importantly, security. Proving correctness in many cases is easy. Proving security, especially for that type of protocol, is always hard. And the advantage of EasyCrypt is also that it can be connected with other languages and tool chains like Rust and Jasmine, for example. So the refined challenge is that how can we prove in EasyCrypt that latter verifier and Joule verifier correspond? Because EasyCrypt doesn't understand just a PDF written paper, and at the same time, not all of the Joule verifier, not all of the Joule could be just copied and pasted from one place to another. And what would guarantee that semantics of this transformation is preserved? One way of doing this is semantic preserving code extraction. So we have 3 layers. On top, we have a layer of rigorous world of formal logic. In the middle, we have a world where lives a detailed and efficient implementation in common languages, like let's say Joule or Rust. And on the lowest level, we have a executable bytecode. So, and from the middle world, we have 2 compilations, one into the theorem prover and another one down to the bytecode. And and under assumption that both of these transformations preserve the semantics, then we can go to our favorite theorem prover, start deriving properties and invariants, and hope, or at least by our assumption, make sure that this invariants and properties would hold for the actual executable code. So in the best world, the process could look as follows. So first, you go to your theorem prover and define the abstract protocol in terms of mathematical abstractions and structures, and then you prove all the properties which are relevant for this protocol, where you prove correctness, security, and so on. Next, you develop the efficient implementation in Joule and Rust, where you kind of keep in mind that later you will be verifying whatever you're writing. And then on the next step, you extract your implementation to the theorem prover, and finally, you carry over the properties from the abstract protocol to the extracted code. In reality, it doesn't work like this. Usually, everything starts, especially for the systems which are already there, that we have the implementation. And then we need to go to the first step and develop the abstract definition of the protocol and derive the properties, and then connect them with the existing implementation, which is a challenge on its own. But what this approach allows is it allows to prove equivalence, or better say refinement, between the low-level code and the high-level definition of the protocol. So you can prove that the low-level code actually is a refinement of the definitions of the abstract protocol. What we're busy with in Matter Labs right now is that we're building the transpiler for a subset of Joule. We're not treating the entire Joule language, but only the so to speak side effect free subset, which doesn't allow you, for example, to copy the stack or copy the bytecode or do any kind of message passing. So this is the subset in which can treat pure functions. And then after doing that, we can start assigning the rigorous semantics to the code which is implemented in, let's say, Joule, and then prove the actual properties. And also note that these techniques could be applied to any protocols written in the side effect-free subset. So for example, we also have preliminary results about precompiled elliptic curve algorithms, which we proved to be correct by extraction. And that's all for me. Thank you. Yeah. I mean, it's very simple to treat. I mean, if you design, if you implement the language, if you implement your protocol already with knowing that you will be verifying it, then the verification. Then implementation usually will be very different. So, and as you're saying, like for the actual running system, it is important that it would be written in the subset, which we can potentially address. So this becomes a node. Like once the transpiler is ready. This becomes a node to the developers. So if you're implementing a protocol, please try to stay in the subset of the language which we can reason about. So that's one thing. Another thing is that in many cases it becomes just if the protocol implementation doesn't follow the good practices for formal verification, then it actually could be simpler to re-implement it and then prove correctness or security. Because of just of the amount of effort. So two functions which are slightly different. I mean, from the programmer perspective, might be completely the same, but you might just fail in derivation of properties simply because there is no right invariance around. So that's definitely has to be considered. Yeah. 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 Yeah, so this is a good question because in this process we essentially assuming we have an assumption that all this transformation are semantics preserving. So if there is if for example your code, if the compiler breaks the abstraction, if it's not doing what you expect it to do on the high level, then there's no guarantees left. Yeah. So from that perspective, and then also another important thing is that as you go through the compilation, even if you proved, let's say, security property for the extracted code, and the extracted code is really similar to the layer in which you implement it. And for example, the UL is very close to the assembly. It's sort of assembly in the head paradigm. You can, if without optimization, you can see what it will compile into. So. But it's still not a guarantee that when you compile it, then a compiler wouldn't do something stupid. I mean, like there is a way to break the abstraction and come up with the bytecode, which would essentially break your zero knowledge property. I mean, it's very unlikely to happen, but it's a possibility. So if you want a full end-to-end guarantees, then you also have to reason on a meta theory level or formally that all these transformations are semantics preserving. But for now, at this stage, we are just interested in designing the toolchain and then keeping this assumption of semantic preservation as the formal assumption.